All right, guys, let's go ahead and let's review limits here. So we'll start off by talking about what a limit is. A limit is the y value a function approaches as x approaches some specified value. As you guys know, in a function, as x is changing, y is changing. And so as x is approaching a specific number, the limit is the y value that we're approaching as a result. So, for instance, on this table here, the x values, as you can see, are getting closer and closer to 1, whether you're coming at it from numbers that are less than 1, or we're getting closer and closer to 1 as we come upwards like this. So, as you guys can see, x is approaching 1 on this table. Now, as we do that, notice that there's no answer for the y when x equals 1. It says error. There's no y value there, but it doesn't matter because a limit is not what the y value equals, it's what the y value is approaching. And so as you look at these y values, what does it look like it's getting closer and closer to? Well, I think it's a pretty good safe to say bet here that when you look at the number immediately above it and the number immediately below it, they're both about 0.33. And so I'd say a pretty safe bet is it could be like 0.33 or it might even be 0.3 with a bar on top and continuing forever. But the y value that we're getting closer and closer to is 0.33. So we could say that y is approaching 0.33. Okay? And the way that we would write that is if I called this function, which we're looking at here, f of x, the way you would write it is like this. You would say the limit of our function as x approaches 1 is 0.33. Okay, that's how you would write it. You could also tell on a graph as we are approaching 1 on the right side, and as we're approaching 1 on the left side, we're getting pretty close to this point right here, which is just slightly above the x-axis. And so a y value of 0.33 is a pretty reasonable guess. Okay? So that's what a limit is. Let's talk about some ways that a limit may fail to exist. One way that a limit may fail to exist is with a jump. And that's whenever your function is approaching one y value from the left, but a different y value from the right. Okay, and so in that case, you would say that the limit as x is approaching whatever number from the left is not the same thing as the limit when x is approaching that same x value, but from the right. In other words, even though they're both reaching the same x value, the y values are not at the same height, and therefore you end up with this jump discontinuity. All right, so that's one way that you can have a limit failing to exist. Another way is with infinite limits. And those happen with vertical asymptotes. So you're going to have a vertical asymptote, and your function will just kind of go up forever, or it could go down forever as it approaches it. But it never really reaches a y value as you approach the x value at the dotted line. As you get closer and closer to that dotted line, the y value just gets bigger and bigger, or smaller and smaller and smaller. It never really reaches any number in particular. And then finally, we have these things called oscillations. These are pretty rare oscillations. They don't happen a whole lot, but basically, you know, let's say as I'm approaching x equals 0, right? My function's doing this, but then it starts to just go crazy back and forth right here. It looks like it touches the y-axis, so it looks like there should be something there. But when it oscillates like that, that intensely at that point, it's never really approaching any specific number because it's bouncing back and forth. So those are three ways that a limit may fail to exist. Now this is how you would write it for a jump discontinuity. For these two, we could be specific on number 2, and I'll talk about that on the next slide, but technically it's okay just to say that the limit does not exist at x equals whatever, c in this case, right? So let's go ahead and take a look at our next slide. Let's talk about infinite limits in a little bit more detail here. All right, there's two kinds of special limits that have to do with infinity. One is infinite limits, and one is limits at infinity. Infinite limits are limits whose the limit itself is equal to positive infinity or negative infinity. Okay? And they are associated with vertical asymptotes. All right, so here's some examples here. If you had a vertical asymptote like right here, and you had a graph that went like this, you could technically say the limit as x is approaching that c value is equal to infinity. And the reason why we could say that is because both the left side and the right side of that limit is going upwards, so we could say infinity. But if they're both going downwards, then we would change that to be something different. We would say now the limit of my function as x approaches c is negative infinity. But I want you guys to understand both of these do not exist. These are limits that do not exist, but we can get a little bit more specific than just saying does not exist. In these cases, we could explain a little bit more detail saying specifically they're infinity or negative infinity. Now I'm running out of space. Maybe you guys will be able to squish it in a little bit better than me, but there's one more. If you have one where it's different on the left and right-handed side, though, like that, in that case, we would just say the limit of your function as x approaches c does not exist. That's all you can do there, because in this case, the limit on the left and the limit on the right are going to different infinities. The one on the left is going to positive infinity because it's going up, and the one on the right is going to negative infinity because it's going down. Now, those are infinite limits. Let's talk about limits at infinity, okay? A limit at infinity is where x is approaching infinity. It could be positive or negative. Okay? A positive infinity means going to the right. Oops, typo there. Going to the right. And a negative infinity means going left. Okay? So a lot of times these could have to do, so I'll put maybe associated with horizontal asymptotes. Okay, so for instance, let's say I had a horizontal asymptote like right here, and let's say that was y equals k. Okay, well, if I had a function that did this, it seems like as I'm moving to the right, the line is wobbling, but it's getting closer and closer to that dotted line. So what I would say then is I would say the limit as x goes to positive infinity, because I'm moving to the right, is it seems to be getting closer and closer to a specific y value of k. Okay, so that would be a infinite limit. So the difference between, a limit at infinity. The difference between a limit at infinity and an infinite limit is infinite limits are y values at infinity. Limits at infinity are where the x is approaching infinity. So it's telling you which direction it's going. It doesn't have to reach a number. It could, but it could also go to infinity. So you could have a limit at infinity like this that goes to infinity. So this would be a limit at infinity, an infinite limit, which is a limit at infinity because both the x and the y values are infinite. Okay, so they can happen together, but there you go. All right, let's go ahead and move on to our next topic of discussion here. Continuity and conditions of continuity. All right, what does it mean for a function to be continuous? Now, this is something you can't really write in your notes. I guess you could if you wanted to, but for a function to be continuous, on, let's say, an interval from point A to point B, you should be able to put your pencil at point A and then just start drawing a line without picking up your pencil until you get to B. And it doesn't matter if you go up and down or anything. It just means there should be no holes, gaps, or jumps. You shouldn't have to pick up your pencil at all. Now, if that's the case, then your line's continuous. But we have to be able to define that mathematically. So what kind of lines are those? We would say that a function is continuous at x equals c if the following holds true. The limit exists, and the y value exists at that point as well, and furthermore, those two things are equal in value. Okay, so what are some ways that we may have some discontinuities? Let's talk about discontinuities now. We've already talked about a couple of them. Jumps. A jump is a discontinuity. The reason for that is because the limit from the left is not equal to the limit from the right. Now, how I'm writing this is very important because this is how you'll justify your answers on FRQs, and this is how they would be written on multiple choices as well. So you're going to want to be familiar. You can't just say jump. You have to be able to write that limit notation down at the bottom. You could also have a hole. Holes are discontinuities. Now, when you have a hole, these are typically removable. And what makes a removable discontinuity is a discontinuity where the limit exists. The limit exists here. Whether you're approaching it from the left or from the right, the limit exists. The problem is that even though the limit exists, the function does not exist at that point. There is no y value. Okay? Then you have these things, and quite honestly, I don't know what they're called. So I'll call them hole dots. I don't know what else to call them, sorry. Hole dots. They're ones where you have a hole and you have a dot, which means, okay, cool, the limit exists because we have, from the left it's approaching the open dot, and from the right it's approaching the same spot. So the limit exists since the left and right limits exist, and the dot exists because there's a solid dot there. The problem is that those y values are not the same. The y value of the limit does not match the y value of the dot. And so those are also a form of discontinuities. The final one that I can think of here are vertical asymptotes. In those cases, which I'll draw a picture of it here, in those cases both the limit and the function don't exist. So it doesn't really matter which one you put, but I think the easiest one is just say that the function doesn't exist at that point. But those are 4 different types of discontinuities. Now, let's talk about one more thing before we change slides here. How to prove a function is continuous at x equals c. You're going to see some problems like this with piecewise functions. So the first thing you want to do is prove the limit exists. Now, for a lot of times with these types of questions, they involve piecewise functions. So when you're doing a piecewise function, the way that you do it is by finding the limit from the left and making sure that it equals the limit from the right. With other functions, there's other ways to do it, which we'll review in a minute. But for now, for piecewise functions, the way that you do is you make sure that the limit from the left and the right are the same. The next thing you do is you prove that the function exists at that point. That's just as easy as plugging it in. Oh, I forgot to put the word exists here. And then 3, check to make sure numbers 1 and 2 are equal. So in other words, whatever you got here and here, make sure that those are equal because the limit has to equal the function. So it's a 3-step process to prove that a function is continuous at a specific point. You need to prove the limit exists, you need to prove the function exists, and then you need to make sure those two things are equal to each other. Okay, let's move on to our next one here. How do you find limits of various algebraic equations and expressions? Let's take a look here. This sheet is very helpful. It's included in the notes section here, and it's also in your notes from earlier this year. It's broken up into two parts, finding limits at a number, which is what C represents, and then on the second page, limits at infinity. I've made two different charts for each one. If you're finding limit at a specific number, try direct substitution first. If you get, and that just means plug it in and see if you get an answer. Plug in your C. If you don't get an answer that way, then we have some strategies. For these types of problems, you'll do these strategies. Or for these types of problems, you'll do this strategy, and so on. There's a lot. Now, if none of these are options or possible for you, then it's probably a non-removable discontinuity, which means the limit doesn't exist. And so you would do this strategy down here, and we'll see them in our notes as we go on. For infinite limits, here are the strategies for those. But beyond that, I'm not going to get into it much more here. Just wanted to reference the sheet with you a little bit. Let's talk about removable versus non-removable discontinuities. Removable discontinuities are those things where the limit exists. Okay? Non-removable discontinuities are ones where the limit does not exist. Okay? Now, removable discontinuities on a graph would include things like holes. I'll put EX here, for example. So it would include holes, okay? Or it could include the whole dots that we talked about earlier. But that's pretty much it. Limits that don't exist would include things like vertical asymptotes. If you're trying to find the limit at a vertical asymptote, that's not going to exist. Also with jumps, that's a non-removable. And oscillations are also non-removable. And so what that means is that with these types over here, you can actually find the limit. You can do either algebra or you can just look at the graph if you have a graph and see what the limit is. But with these guys over here, the limit doesn't actually exist. So the answers could be one of three things. They could be infinity, negative infinity, or does not exist. One of those three things. But the limit just simply does not exist. Okay, so in those cases, that's the difference between removable versus non-removable discontinuities. All right, last slide. Let's talk about the intermediate value theorem. So first of all, I want to give you the common sense understanding of this theorem, and then I want you guys to give you the formal thing to remember about it. So here's the common sense thing. You don't need to write this, you just pay attention, but here it is. If I'm going from point A to point B, and my question is, at some, like let's say this is at a height of, ground level. Let's say I'm on the ground. And let's say that this up here is the third story of a building. Okay, so the question is, at some point, would I have to go through the second story to get there? And the answer is yes, you would. If you're going from ground level to the third story, going up the stairs, at some point you're going to have to cross the second story, right? It just makes sense. So here's the intermediate value theorem. It says if you have a continuous function and you're going from a lower point to a higher point and you want to know, is it possible to reach that y value right in between? Well, the answer is yes. At some point that has to actually happen. But it's only true if it's a continuous line, because what if there was a hole here? Well, now all of a sudden we went through a wormhole and we got to skip the second story somehow. But that doesn't make sense with my example, but I'm just being silly. But you got the idea there. It has to be continuous, all right? And so here it is. Let me draw a picture and write a sentence for you. So here's the intermediate value theorem. Since f of x, the function, is continuous on the interval from a to b, there must be, oh, actually, let me back up, and goes from a height of f of a to a height of f of b there must be some value c such that so c is going to be in here. It's got to be in between a and b. I'll put that up here. There must be some value c such that f of c equals k, so long as k is in here. So there has to be some place where there's an x value that gives you a y value that would be in between those two y values. Okay, and that's the intermediate value theorem. So since f of x is continuous and it goes from f of a to f of b, there must be some value c such that f of c equals k. You have to make sure that k is actually in between these two numbers. That means that c will have to be in between these two numbers, and it has to be continuous. Okay, so things to check for. First of all, you have to make sure it's continuous. Second of all, you have to make sure that k is in between f of a and f of b. Now, it doesn't really matter whether f of a or f of b is bigger. Just make sure that the k value that you want has to be in between those two y values that they gave you. And as an added little rule, the endpoints can't be equal to each other. But that's kind of obvious, because if these were equal to each other, then k couldn't possibly be between them. So that's kind of a moot point. So I usually just kind of leave that one out. All that really matters, I mean, we can add it here just in case they ask like a special kind of question. F of a cannot equal f of b. But so long as these three criteria are in place, then that c value would have to exist. Okay, so that's the intermediate value theorem. We'll go ahead and stop there, and I'll let you guys go ahead and begin your worksheets, and we'll talk to you later.